Hi, my name is Nimer Mansoor, and in this talk, I will present our work on detecting critical bugs in SMT solvers using Blackbox mutational fuzzing. Satisfiability modulo theories, or SMT in short, is the decision problem of automatically determining whether a logical formula is satisfiable with respect to a background theory. An SMT instance is a formula in first-order logic which generalizes a Boolean set formula by supplementing Boolean variables with predicates from a set of theories. For example, a predicate could express a linear inequality over real variables, in which case its satisfiability is determined using the rules of the theory of linear real arithmetic. Other theories include bit vectors, arrays, integers, strings, to name a few. Let's now represent this formula in the form of a Boolean expression tree. This formula is satisfiable over the theory of real arithmetic because there exists a satisfying assignment to the variable x, for example 5.4. Let's now add a predicate to this formula. This formula is also satisfiable because of the existence of a satisfying assignment to variables x and y. Adding y greater than 9 makes the formula unsatisfiable due to these contradictory predicates, because y cannot be greater than 9 and less than x if x is less than 9. SMT solvers are tools for evaluating the satisfiability of SMT formulas, and they are quite complex in their implementation using many heuristics and simplification techniques. After all, they are working with NP-hard and sometimes undecidable problems. There are already many SMT solvers available, each with their own strengths and weaknesses. And these solvers are extensively used in formal methods community, from program verification to automatic test case generation to program synthesis. An incorrect result from an SMT solver can invalidate the result of these tools, which can be catastrophic in safety critical domains. This table shows the classes of bugs that may occur in an SMT solver. These values represent the ground truth of an SMT instance. And these are the possible results that can be returned by a solver. Bugs in class A and B are soundness bugs. For bugs in class A, the solver returns unsat for an instance that is satisfiable. These bugs are known as reputational soundness bugs in the SMT community. Class B refers to bugs where the solver returns sat for an unsatisfiable instance. A solver is incomplete if it returns unknown for an instance that lies in a decidable theory fragment. We categorize such bugs in class C. Finally, bugs in class D indicate crashes where solver does not return any result. We call bugs in class A as critical for two main reasons. Such bugs may cause unsoundness in program analyzers that rely on SMT solvers. For example, a software verifier that checks the reachability of an error location by querying an SMT solver. If the solver unsoundly proves that the error is unreachable, for example unsat while checking the feasibility of an error trace, then the verifier will verify incorrect code. Second, it is much harder to safeguard against these bugs compared to other classes. Specifically, consider that when an instance is found to be sat, the solver typically provides a model that is an assignment to all the free variables in the instance such that it is satisfiable. Therefore, bugs in class B can be detected simply by evaluating the instance under the model generated by the solver. If this evaluation is false, then there is a B bug. Bugs in class C are detected whenever the solver returns unknown for an instance that lies in a decidable theory fragment. And bugs in class D are detected whenever the solver crashes. So how can we generate interesting new SMT instances that can detect critical bugs in SMT solvers? One way is to use a grammar to generate syntactically valid SMT instances from scratch. Another idea is to somehow transform existing instances. But then we have this oracle problem, that is, how can we determine the satisfiability of the newly generated or transformed SMT instance without relying on a solver? We propose a general black box fuzzing technique that does not rely on a grammar to synthesize new instances from scratch. Instead, it takes inspiration from mutational fuzzers like AFL and generate new instances by mutating existing ones called seeds. Given a seed SMT instance, our approach works in 3 phases. Phase 1 is called seed fragmentation, Phase 2 formula generation, and Phase 3 instance generation. And of course, the output is n new SMT instances that can be used to test the SMT solver. Let's start with Phase 1. Seed fragmentation. Imagine an SMT instance with some assertions. Each assertion contains a logical formula such as f shown here, which is potentially made up of Boolean subformulas, such as f1, f2, f3, and so on. Let's represent f as a binary Boolean expression tree. Suppose f1 is a predicate y greater than x, f2 x greater than 2, and f3 x less than 10. As a first step, we generate a random assignment for all the free variables in the seed instance. Let's say 11 to x and 10 to y. Next, we recursively evaluate all the subformulas on these random variable values to populate an initial pool. So for example, formula f3 on this value of x is false, because x is not less than 10. So we will copy f3 to the false set in our initial pool. Next, f2, which is x greater than 2, is true, and hence we copy this formula in the true set. Subformula f2 or f3 is also true, and we also copy it to the true set. Formula f1 is false because y is not greater than x, and we copy it to the false set. And finally, formula f is false and hence is copied to the false set. So in essence, Phase 1 just recursively evaluates every subformula in the binary Boolean expression tree of f and copies them to an initial pool in either a true or false set based on their evaluation. Once we have our initial pool, we can move on to Phase 2. Formula generation. In Phase 2, we construct another pool called the construction pool. We use the formulas in the initial pool to build new and more complicated formulas. For example, we select f2, which is in the true set, negate it, which now makes it false, and move it to the false set in the construction pool. Next, we take f2 or f3 from the true set, disjunct it with f1 from the false set, and move it to the true set in the construction pool. We can also use the constructed formulas from the construction pool. Here, we disjunct 2 false formulas, negate them, and then move the new formula to the true set. Let's do this for a few more times. We can do this as many times as we like, but let's stop here. So in essence, the second phase enriches the set of existing formulas in the initial pool to generate new ones without requiring a complete grammar for all syntactic constructs. Instead, we use a minimal but functionally complete grammar for Boolean formulas. This significantly simplifies formula generation without sacrificing expressiveness. Now that we have our set of initial pool and construction pool, we can move on to Phase 3, instance generation. In Phase 3, we create a new SMT instance by randomly selecting formulas from the initial and construction pool. Let's select 4 formulas and export them to create a new SMT instance. Note that the formulas that were selected from the fault sets are negated in the SMT instance. This SMT instance is satisfiable by construction. This is because all the formulas that are now asserted in this instance are true on random values we selected in phase 1. Hence, we know that there exists at least one assignment to all the variables in all the formulas in this instance, which makes this instance satisfiable. If we now feed this instance to an SMT solver and the solver returns unset, then we found a critical bug. In practice, our fuzzing technique often generates bug-revealing instances that are very large. Whereas to trigger the bug, we either only need a small portion of the formula or a combination of some small subformulas. Adapting established minimization techniques based on delta debugging seem like a natural fit for this cause. However, the special nature of critical bugs complicates this task in comparison to other classes of bugs such as crashes. For minimizing crash bugs, it is sufficient to minimize the original instance by, for example, dropping assertions while preserving the crash. In case of critical bugs, the behavior that should be preserved is a bit more involved. That is, the instance should be minimized such that the buggy solver still returns unset while the ground truth remains set. This requires either a satisfiability preserving minimizations or a second trusted solver that can act as a ground truth oracle by rejecting minimizations that do not preserve satisfiability. However, a second trusted solver is not always available, for example, in case of new theories or solver-specific features and extensions. To overcome these limitations, we developed a specialized minimization technique that directly leverages our fuzzing procedure. We feed the buggy instance back to our fuzzer, but now we put limits on the size of new formulas and instances in phase 2 and 3. Formulas and instance size should be less than the original bug-revealing instance. The fuzzer will now produce smaller satisfiable instances, and if the solver returns unset on one of these instances, we repeat the process again until the bug-revealing instance can no longer be minimized. We have implemented this approach in a tool called Storm, which is open source and publicly available on GitHub. You can also get more information about Storm and the critical bugs it detected on our website. Now, to evaluate the effectiveness of Storm, we selected 7 popular SMT solvers which support the SMT lib standard and regularly participate in the international SMT competition, SMT Comp. In addition to these solvers, the developers of Z3 asked us to test a new arithmetic solver. We refer to it as Z3AS, which they had been preparing for the last 2 years. They also asked us to test Z3's debug branch. We refer to it as Z3DBG. For each solver, we identified well-supported logics based on its participation in SMT Comp 2019. In certain cases, we also added logics identified as error-prone by the solver developers, such as quantified free-floating points. We used as seeds all non-incremental SMT lib instances in SMT Comp 2019. We also used all SMT lib instances in the regression test suites of CVC4, Yikes, and Z3. So now we ask, how effective is Storm in detecting new critical bugs? This table shows the critical bugs detected by Storm. We list Z3STR3 separately as it is not the default string solver in Z3. The second column in this table denotes whether bugs were found in the incremental mode of a solver, which essentially corresponds to a different solver variant. The third column lists the logics in which bugs were found. And the last column shows the number of bugs. Overall, Storm found 29 critical bugs in 3 mature solvers or 9 solver variants in 15 different logics. All these bugs were previously unknown, unique, and confirmed by solver developers. In addition to bugs in this table, Storm was also able to detect known bugs as well as other issues that is of class C and D as a byproduct, which we do not report here. We have received some very positive feedback from the developers of different SMT solvers. One of the developers of Z3 string solver reached out to us and thanked us for reporting the soundness issues in Z3 SDR3. He further says, "I'm wondering if you have a larger collection of string instances that you could share with me for benchmarking and performance testing." Another Z3 developer said, "Your work is super cool, thorough, meticulous, and pragmatic. Further, the paper is beautifully reasoned and written." A Yikes developer said that it is especially useful to have the ability to test the incremental mode of solvers. Commenting on one of the bugs, another Yikes developer said that it was easy to fix and an obvious mistake in retrospect, but it wasn't part of Yikes that had probably not been exercised much. The other one was much more tricky to trace and fix. It was related to a combination of features and optimization in the E-graph, not localized to a single module. Another SMT developer reached out to us and said, "I hope your paper becomes a standard reference because it educates potential SMT users on the different severity of different classes of bugs." In conclusion, we presented a simple and effective Blackbox mutational fuzzing technique to detect critical bugs in SMT solvers. These solvers are key components in many state-of-the-art formal methods tools. We implemented the technique in a tool called Storm, which is open source and publicly available on GitHub. Storm has detected many critical and previously unknown bugs in many theories across mature and widely used SMT solvers.